Okay, now I've said it many times already, strong electrolytes are strong acids, strong bases, and ionic compounds. But I didn't explain correctly what I meant by ionic compounds. First, let me look at this word here, salt. Salt in chemistry is basically another word for ionic compound. And when I talked about strong electrolytes being ionic compounds, they have to be ionic compounds that are actually soluble in water. Not all ionic compounds actually dissolve in water. Water is great at dissolving ionic compounds, but it's not strong enough to dissolve all of them. So this is where we're going to have this little chart here. And this will be given to you on any in-class test. And let's look at how to use this. The top part are soluble ionic compounds, and these are going to be compounds containing these ions, and over here are the exceptions. So nitrate and acetates are always soluble in water. Chlorides, bromides, iodides are usually soluble in water, except when combined with silver, mercury, and lead. Sulfate is always soluble except with strontium, barium, mercury, and lead. And these are insoluble ionic compounds: sulfides, carbonates, phosphates, and hydroxides. Here are the exceptions. Basically, anything that is combined with ammonium is always going to be soluble. Ammonium really should be up here as well. And then sulfide is insoluble except when it's combined with ammonium. The alkali metal cations, which are the first column of the periodic table, lithium, sodium, potassium, rubidium, and cesium, and then also these members of the second column of the alkali metal family. Oops, alkaline earth, sorry. Carbonates are always soluble except when combined with ammonium, and sodium, lithium, potassium, rubidium. Compounds of phosphate are insoluble except when combined with ammonium and lithium, sodium, potassium, and rubidium. And then hydroxides are insoluble except the alkali metals, which are lithium, sodium, potassium, rubidium, and cesium, and ammonium, and then these three here. So you don't have to memorize this, you just have to know how to use it. So go ahead and pause the lecture, take a look at that chart in your table that has the list of soluble and insoluble ions, and see if you can determine whether each one of these 6 compounds is soluble or insoluble in water. So our first compound was calcium chloride. Here's our ion chloride right there. It's not an exception. So calcium chloride will be soluble, and we would put an AQ here. Actually, let me change the color of my pen. Okay, our next compound, calcium sulfate. Here's sulfate, and it is soluble, and calcium is not an exception. So calcium sulfate is going to be AQ in water. And what that means is this is going to dissociate into calcium and sulfate ions, and this will dissociate into calcium and 2 chloride ions. Here's calcium phosphate. Let's look at here's phosphate, and it is insoluble, and calcium is not one of the exceptions. So calcium is not going to be AQ in water. It's going to be solid in water. And let's look at this, copper nitrate. If I look at my chart, I don't see copper listed anywhere, but I do see nitrate, and any compound that has nitrate is always soluble. So that's going to be AQ in water. The AQ means dissolved. Let's look at copper sulfide. Again, copper's not here, but sulfide is. It's insoluble, and copper is not one of the exceptions. So this is going to be solid in water. And ammonium hydroxide, here's hydroxide, but ammonium is one of the exceptions. It's in the insoluble category, but because ammonium is an exception, then this is going to be AQ, meaning that my ammonium and my hydroxide are going to dissociate. Now this brings us to a type of chemical reaction known as a precipitation reaction. And this occurs when we mix two solutions together that, when they are mixed together, form an insoluble compound. This insoluble compound is a solid, and it's known as a precipitate. So here I'm pouring a solution that's colorless into another solution that is colorless, and as soon as the two mixtures hit one another, a solid forms. These reactions are very, very quick. Precipitation reactions are a type of what are known as metathesis, exchange, or sometimes double replacement reactions. And the word metathesis comes from a Greek word that means to transpose. So let's look at how to figure out what the products of a metathesis reactions are, and we're going to start off with a precipitation reaction as an example. Now, in chapter 3, I didn't care too much if you had your states listed or not, because we were basically just focusing on balancing an equation, and the state had no bearing on whether an equation was balanced or not. But in this chapter, the state is going to be very, very important, so you're going to need to get into the habit of writing the state down for every chemical involved in the chemical reaction. To figure out the product of any metathesis, exchange, or double replacement reaction, what we do is we exchange the ions. So silver nitrate, AQ in a solution, reacting with potassium chloride, AQ in a solution. If they react, they're going to switch their ions. The positively charged silver will now combine with the negatively charged chloride, and the negatively charged nitrate is going to combine with this positively charged potassium. So we're switching ions. Once we switch ions, we look at our chart and see if the formed compound is insoluble, meaning it will be an S, or if it is soluble, meaning it's AQ. So let's look at an example. Here we have lead 2 nitrate reacting with calcium hydroxide. How will we know what the products are and if a precipitate will form? Well, what I do is I take apart the ions in each chemical and I put them on top of one another like this. Here's lead 2 nitrate. My lead has a 2+ charge and my nitrate's at -1. And I know my lead has a +2 charge because I have 2 nitrates, and nitrates always have a -1 charge, so my lead has to be +2. Calcium always has a +2 charge, and of course hydroxides have -1. This 2 means I have 2 nitrates and I have 2 hydroxides. So after I separate out the ions in each compound, then I just make a little cross like this. My lead was originally with my nitrate, and now it's going to go with my hydroxide. My lead has a +2 charge, so it's going to need 2 hydroxides to counter out that +2 charge. My calcium was originally with the hydroxide, and now it's going to go with the nitrate. And I need 2 nitrates to counteract that positive charge on the calcium. After I figure out what my products are, I look at my chart to see if either one would be a precipitate, meaning is it insoluble. When I look at my chart, I see that nitrate is always soluble, but hydroxide is insoluble. And calcium was an exception, so my calcium hydroxide was soluble, but lead is not. So my lead is going to be a precipitate. This hydroxide is insoluble. That's hard to tell, but that is a solid right there. And then this remains, oops, I'm running out of room. This remains AQ. And I said it's very important to keep track of your states here, because this is going to tell you if a chemical reaction occurs or not. And in solution chemistry, we really do need to pay attention to exactly what species are present, and their states, solid, liquid, gas, or aqueous, and that's going to give us some clues as to the reactivity.